Love technology? Subscribe to Explainer 99.
Welcome to this explainer. Today, we're taking a machine with a magnetic field tens of thousands of times stronger than the Earth's and breaking down exactly how it transforms invisible physical forces into stunning medical images.
If you've ever had an MRI, you definitely remember the experience, right? The tight space, those incredibly loud banging noises. But what's actually happening in there? How does a giant magnet manage to look right through your skin to see soft tissue without using any harmful radiation and perfectly map out the intricate details of a beating heart or a torn ligament?
Here's our roadmap for today: the core physics, RF pulses, gradient coils, safety protocols, and the future of MRI. Let's dive in.
Section 1. The core physics, starting with the main magnet.
Think of the MRI as a perfectly nested symphony of hardware. On the absolute outermost layer, you've got the main superconducting magnet. This creates a massive, uniform, and totally static magnetic field. Nestled just inside that are the gradient coils, and tucked even further inside are the radiofrequency, or RF coils. It is a highly organized, layered cylinder.
Now, since your body is mostly water, it's absolutely packed with hydrogen protons. Normally, these tiny guys are spinning around with their axes pointing in totally random directions. But the second you slide into the bore of that giant magnet, everything changes. It's like billions of microscopic compass needles suddenly snapping to attention. The sheer power of the main magnetic field forces these protons to align, essentially turning them into our biological canvas.
Moving right along to Section 2, RF pulses and how we knock those protons down.
So we've got our protons aligned, right? The crucial next step is getting a signal out of them. The sequence here is beautifully simple. Step 1, the main magnet holds them in alignment. Step 2, the machine fires a highly specific radiofrequency pulse. This pulse is tuned exactly to the protons, which temporarily knocks them right out of their alignment. Step 3, the pulse turns off, and as those protons snap back into place, they release their own tiny radio signal. Finally, Step 4, the scanner reads that released energy, and boom, that energy is the raw data of your medical image.
Section 3, Gradient coils and 3D spatial encoding.
Remember those gradient coils nestled inside the main magnet? These are essentially loops of wire or thin conductive sheets. Now, unlike the main magnet, which is static and always on, these gradient coils are turned on and off incredibly fast. In fact, that rapid switching, that's exactly what causes that loud, rhythmic banging noise you hear during a scan. Ultimately, they act like a highly precise 3D GPS system for your protons.
And that brings us to a really foundational concept called spatial encoding. To know exactly where a signal is coming from, we absolutely have to distinguish a proton in, say, your left shoulder from one in your right elbow. The gradients do this by slightly distorting the main magnetic field across your body. Since a proton's frequency is directly tied to the magnetic strength it experiences, varying the field means protons in different areas spin at slightly different frequencies. It's kind of like a massive choir where every single person is singing a slightly different note, allowing you to pinpoint exactly who is standing where.
So how does it map all three dimensions? Well, there are three distinct sets of gradient coils, driven by independent power amplifiers for the X, Y, and Z axes. If the scanner wants a transverse slice, cutting horizontally across your body, it fires up the Z gradient. For a coronal, or front-to-back slice, it uses the Y gradient. And for a sagittal, left-to-right slice, it hits the X gradient. The craziest part? The scanner can isolate any specific slice of your body, or even complex oblique angles, without ever moving a single physical mechanical part. It's all done invisibly, using only magnetic fields.
Section 4. Safety protocols and the physical stakes of an MRI. Now, as the source material strongly emphasizes, all this invisible power comes with very real physical stakes. The static field and switched gradient magnetic fields can exert dangerous forces on metal. Keep in mind, the main magnet is always on, literally always, and it is overwhelmingly powerful. Any interaction with ferromagnetic metal can turn this miraculous diagnostic tool into a very deadly hazard.
This is exactly why rigorous safety screening is a literal lifesaver. Items like older legacy pacemakers can be outright destroyed, aneurysm clips in the brain can torque or shift under that extreme magnetic force, and embedded shrapnel can become a dangerous internal projectile, no joke. But it's actually not just about the magnetism itself. The rapidly changing gradient fields and RF pulses can induce electrical currents. That means things like deep brain stimulators or long metallic orthopedic hardware can dangerously heat up inside the scanner, potentially causing severe internal burns.
Finally, Section 5, the future of MRI and next-gen technology.
When you look back, the evolution here is just staggering. From Paul Lauterber's 1973 breakthrough on gradient imaging, which totally earned him a Nobel Prize, by the way, to the introduction of massive superconducting magnets, the field has moved incredibly fast. Today, we're seeing the integration of artificial intelligence to process images faster and clearer than ever before, alongside advanced techniques like quantitative susceptibility mapping. Looking ahead, the future points straight toward highly sophisticated, low-field portable scanners that can be wheeled right to a patient's bedside, fully powered by deep learning diagnostics.
To really put the sheer power of this technology into perspective, your standard clinical scanners usually operate at about 1.5 to 3.0 Tesla. But we are now pushing the absolute limits with ultra-high field 7 Tesla machines. These are absolute behemoths used in advanced brain mapping to see microscopic structural details. Meanwhile, at the exact opposite end of the spectrum, incredibly clever software is allowing us to build extremely low-field portable setups that most experts thought were physically impossible just a decade ago.
We've gone from manipulating the random spin of a tiny water proton all the way to massive superconducting magnets mapped in 3 dimensions by totally invisible gradient fields. It's wild to think about. As AI and advanced tissue mapping continue to push the boundaries of what this incredible hardware can actually see, it leaves us with one thrilling question to wrap up on. What hidden worlds inside the human body will we map next?